Okay guys, so in the last two classes we looked at how we might represent numbers using bits. We started by looking at a single bit and how it could have some kind of meaning depending on what we decide to associate with that meaning. We saw that if you combine bits you can have them mean a number of different things. But the number of possible different things you can represent with a fixed number of bits is limited. And the more bits you have, the more things you can represent. We saw how you can use the binary counting system to represent positive integers. We also saw that representing negative numbers was a bit more complicated. We saw 1's complement and 2's complement. And we also saw how you could represent a range of values, but the different schemes had different features. I think we kind of concluded that 2's complement was pretty damn handy because it had a number of features, in particular that you could apply binary addition to the negative numbers and you'd get the right answers. I also mentioned briefly, but we didn't really discuss it, is that for representing decimal numbers, or real numbers, we'd use the IEEE floating point standard, and you can look that up. What we're going to look at today is how we're going to represent text using bits. How would you represent a message in letters? How do you represent letters with text? In reality, most of the time we're concerned with how do you store media on some storage device using bits. But conceptually, it's easier to imagine that we're transmitting a message from A to B. So you have a transmitter, you have a receiver, YAN, and you have some scheme for exchanging messages between the two places. So sometimes it helps to visualize things that way. Now, so how would we represent text with bits? So how many bits do you need to represent a character? You recall when we decided we wanted to give each student in the class their own unique bit code. 1001, what did we decide? What did we figure out?
5 bits.
That depending on how many you have, you need a certain number of bits. The first thing you need to figure out is how many different possibilities there are. So how many characters are there? How many characters do we need? Well, if you think about it, we have like 26 letters from A to Z. If we had a system where we wanted to distinguish between uppercase and lowercase, we'd need another 26. I think Morse code, for example, doesn't care whether it's uppercase or lowercase. I mean, you're supposed to figure that out. But in a text document, for us, uppercase and lowercase is important. In German, uppercase and lowercase is important. We probably want some numbers. We'd have the digits 0 to 9. There's another 10 there. And we could say then that the various, punctuation and, funky characters, maybe there's another 30 there. I would say that 92 characters would be plenty. So if we had 92 different characters, how many bits would we need? With 5 bits, how many possible? We saw that with 4 bits, wasn't it? You could represent 16 different possible things. With 5 bits, you could represent 32 different things. With 6 bits, you could have 64 different things. With 7 bits, you could go as far as 128 different things. So I think if we want to have a character set with 92 characters in it, we'd need to use 7 bits. We wouldn't have enough at 6. Now, knowing that 6 bits would give us 64 characters, we might decide, well, actually, look, we'll have 26, and 26 is 52, and 10 digits is 62, and maybe we'll just have a full stop and a question mark or something. We might decide that we really wanted to fit in that smaller number of bits. But anyway, let's say we're going for 92. So we could devise a table like this, where we list out the possible combinations of bits. And then that tells us where we put the characters. So we'd read this then, starting with the bits here first, and then over here. So A would be 0, 0, 0, 0, 0, 0. I would be 0, 0, 0, 1, 0, 0, 0. And so uppercase C would be 0, 0, 1, 1, and then 1, 0, 0. So that's how we'd read a table like this. It's just easier to express it in this format rather than have 0, 0, 0, 0, 0, 0, 0, A, and then 0, 0, 0, 0, 0, 0, 1 is B, and 0, 0, 0, 0, 0, 1, 0 is C. You know, this is a more compact form, but there's no mystery of how to read the table. So what is uppercase Q in this scheme here? 0, 1, 0, 1, 0, 1, 0. And number 2 is 0, 1, 1, 0, 1, 1, 0. Now, I just made that up, like. I mean, we could have put the uppercase letters first and the lowercase letters next. Or we could have done like big, small a, small b, big B, small c, big C, small d, big D. That would have worked. That would actually be quite clever, in fact, because you could maybe just take, if you were in a hurry, you could maybe just ignore the last bit or something. I don't know. You could do cool things with that. Anyway, I digress. So here's a system that I just made up. And as we'll see in the next class, maybe, there are many such systems. But in general, in order to decode a sequence of bits, the table that maps the bits to characters has to be available. So if I'm going to transmit messages from here to there, and it's going to be 7 bits per letter, well, myself and the receiver, we have to agree on what the bits are going to mean. So we'd have to have this table. So a bit like Morse code, where the transmitter and the receiver have agreed that this combination of dots and dashes means that. Once you have that standardization, then you can transmit messages. So we'd have to have an agreed table. Some of the earliest forms of encryption would have been schemes where essentially the table was the secret. And the German Enigma machine worked essentially by every time you press the key, the table changed. And there was lots of mechanical goings on there to make all that work. But you do need some sort of standard between you and the receiver, between the transmitter and the receiver, in order to make that work. Now, so I have an exercise for you. Okay. So, this is a map of some place after the zombie apocalypse. Okay, And so the remaining humans are holed up in outposts. Alas, outpost 20 has fallen to the zombie horde. And it turns out that inside in the compound 19, inside in outpost 19, they're able to control traffic lights at the edge of the town that can be seen by the other outposts nearby. And so they've been using Morse code to send messages back and forth. However, there was a very clever computer scientist among their ranks. But in the last attack, alas, he was lost. And all they have left are his notes. And he had told them that there was a much more efficient way to send the messages using the traffic lights. So it's a pair of traffic lights on the edge of town, and each of the lights can be controlled individually. So, in a land where zombies roamed the world, he discovered the key to communication. But alas, he was killed. And now his friends have to, through cooperation and imagination, figure out what he was talking about. So they've sent out a message. They didn't quite get what this 23 multiplied by 23 equals 64 was about. They didn't understand that. And they know that the 23 by 23 was the key to figuring out this scheme that was much more efficient than Morse code. But that's all they have are his notes. And so they're looking for help from you, the last remaining humans, to save civilization. So, I want you to come up with a scheme for transmitting messages using this pair of traffic lights on the edge of town. Now you can control the lights individually, do you know what I mean? You can have the top red one on and the middle yellow one on if you want. But I think you have to figure out what this 23 by 23 equals 64 is. That's the key. So you can figure that out, you're laughing. So, off you go. Save humanity from the zombie horde. In groups of maybe 4 or 5. Okay?